Unit Overview. In this unit, we turn to another important data structure called queue. We shall study characteristics of various types of queues and related operations. We shall also examine various applications of queues in daily life, computer science, and other disciplines. For each type of queue, we would study different ways of implementing queue data structures using arrays and linked lists. Objectives. After studying this unit, you should be able to define the logical structure of a queue, understand the operation involved in adding elements to a queue and removing items stored in a queue. Describe circumstances when underflow and overflow conditions occur in manipulating queues. Describe simple applications which make use of queue data structure. Distinguish between regular queues, circular queues, priority queues, and dequeues. Understand the array-based implementation of different variants of queues. Understand the linked-based implementation of regular queues and dequeues. Compare the relative advantages and disadvantages of different implementations of queue structures. Choose appropriate implementation on the basis of performance and efficiency. Introduction to queues. A queue is a collection of homogeneous items in which new items can be added at one end and current item removed from another end. The end at which an item is removed is called front, and the other end at which the item is appended is called rear or back of a queue. A queue acts like a tunnel, such that an element entering first comes out first. For this reason, a queue is commonly called first in, first out, FIFO structure. A FIFO queue is sometimes called a regular queue to distinguish it from other variants of queue. Figure shows an example of queue which contains alphabets A through H. The arrows mark the front and rear ends of the queue. Notice that there is only one entry and one exit point. This arrangement implies that only the front and rear elements of the queue can be accessed directly. The middle elements are not accessible, and their order is preserved in all operations on a queue. This feature is illustrated in figures. In the first example, letter A is removed and the front pointer moves to the element B. In the second illustration, letter I is added and rear pointer is moved to the newly entered alphabet. Notice that after addition and deletion, the order of elements B through H remains unaltered. Remember, as with other data structures, the elements of a queue must be homogeneous. This means that all items must be of the same data type and size. However, elements may not necessarily be numeral, character, or other primitive types. Depending upon the application, a queue data item can be records, consisting of several fields, or even more complex data structures. For example, a queue representing the telephone directory might contain subscriber's name, address, and telephone number. Application of queue. Various forms of queues are often observed in our daily life. Some familiar examples are a line of persons waiting for their turn to board a bus, utility bill payers standing in a queue to make payment at bank counter, a fleet of cars and buses lined up at a toll booth on motorway. In all of these examples, the principle of first come, first served applies. All new arrivals must join at the rear of the queue. Different types of queues are extensively used in computer sciences and other disciplines. Queues provide an effective buffering mechanism for synchronizing the operation of slow devices with fast CPU. For example, the keyboard is a slow device compared to other processing units of a computer. Thus, when we enter characters at a keyboard, the computer system holds these characters in a buffer, in the order in which the characters are typed in. The queue is later processed by CPU or displayed on the screen. Likewise, in printing jobs, the computer sends lines and images faster than the printer can print them. The lines and pixels are held in a queue for the printer and processed in the order in which they enter the buffer. Also, when a printer is shared by several computers, or when a desktop computer sends several printing jobs, each job is inserted at the rear of print queue. Queues are frequently used by operating systems for sequencing and scheduling of events, messages, processes, and subtasks in time-sharing environment. In operation research, queuing models are used to analyze and optimize the service times by minimizing the waiting time and reducing service cost. Operations on queues. Some common operations on a queue include creating a queue, adding new item to a queue, removing an item, checking if queue is empty, checking if queue is full, determining number of elements in a queue, accessing the first added item without removing it from the queue, destroying the queue. Creation of queue is always the first operation in any application. This step simply creates an empty queue. The add operation inserts a new item into the rear of a queue. If the space allocated for the queue is already utilized, this results in overflow condition. The add operation is also called enqueue, insert, or append. The remove is another primitive operation associated with the queue. This operation removes the item at the front of the queue. If queue is empty, an underflow condition occurs. To avoid this problem, queue must be checked for emptiness. The remove operation is also known as dequeue, delete, or serve operation. The operation returns the retrieve item to the calling application. The isEmpty operation returns true if the queue is empty and false otherwise. It is generally applied to check the underflow condition. The isFull operation checks if the queue currently contains the maximum number of allowed items. If the limit is reached, the operation returns true and false otherwise. The sizeOf operation returns the number of elements currently held by a queue. The peek operation returns the item that was last added to the queue. However, unlike the remove operation, the item is not deleted from the queue. The destroy operation removes all elements of a queue and releases space allocated to the queue. Implementation of queue. There are two approaches to the implementation design. A queue can be stored in static array of fixed size or dynamically allocated memory using linked lists. Both schemes have their advantages and disadvantages. In general, the queue data structure is implemented as a C++ class which has the composition as shown. Note that a class Q includes two integer variables, front and rear, which monitor the exit and entry points of a queue. The coding details of class methods add, remove, isEmpty, isFull, peek, and destroy are covered in subsequent sections. Array-based implementation of queue. In array-based implementation, an array is used to store data items in a queue. For example, if we may want to store names in a queue, the declaration might look like this. This declaration is meant to store 100-character strings called queue names. The maximum size of a data item is assumed to be 20. Remember, in C, C++, the character strings are declared as a two-dimensional character array. Also, we need to declare two integer variables, front and rear, to indicate the position of an item to be added or to removed from the array. The variables are initially set to -1. As data are added to the queue, front and rear are incremented by 1. Figure shows an example of array-based implementation to hold up to 10 elements of a queue. As shown, the queue holds 5 characters Q through U, which have array indexes from 1 to 5. The variable front contains 1, which is the current position of the elements at the front position, and variable rear contains 5, which indicates the last position of the queue. The next figure shows a full queue. Performance of array-based implementation. As insertion and deletion operations in the array are controlled by the variables front and rear, the performance of these operations does not depend solely on the number of data items in the queue. As such, the running time of both enqueue and dequeue operations is O of 1. Limitation of array-based implementation of queue. A major limitation of the array-based design is that the maximum size of the queue must be specified in advance. If a user needs a queue to process fewer items than the prescribed size of array, a lot of memory space would be wasted. Another serious drawback of the array-based scheme is that the slots created by removing of items from an array cannot be filled by the new incoming items. Consider the queue shown. In this example, the array elements with indexes 0, 6, 7, 8, and 9 do not hold any queue items. Since elements can only be added at the rear end, the array elements with the index 0 cannot be filled with the new element. Further, as new items are added or current items deleted, the entries in the array shift to the right. This behavior is shown in figure. After P, Q, R have been removed and U, V, W are added. Ultimately, if all the elements are removed, both front and rear would move to the rightmost position. It would result in a situation in which the queue is empty and yet no new elements can be added to the queue. One possible solution to this problem is to shift all the elements to the left whenever an item is removed from the queue, as shown. The new elements can always be added to the vacant position on the right. Further, we would no longer need front pointer because the elements of array index 0 will always be the first element of queue to be deleted. However, for very large queues, the process of shifting all the elements at each deletion would time-consuming. It would have a running time O of n for a queue of size n. Thus, though the alternative array representation would be space-wise economical, it would not be time-wise efficient. A satisfactory solution for efficient utilization of array space is provided by wrapping round the front and rear pointers to the beginning of the array. This strategy is called circular implementation. The corresponding queue is known as circular queue. We shall examine circular queue later in this unit. Linked list-based implementation of queues. We have seen that array-based implementation does not provide a satisfactory solution to handle queues of variable sizes. An alternative approach using linked list overcomes these problems by dynamically allocating storage space. In this implementation, elements of queue are stored as nodes of a linked list. 2 pointers are needed to mark the beginning and end of a queue. These are referred to as front and rear pointers. Figure shows an example of a queue implemented as a linked list. Implementation of NQ and DQ operations is rather straightforward. The NQ simply adds a node at the tail of the linked list. The DQ operation removes the first node of the list. The detailed procedures for adding and deleting nodes of a linked list were discussed in the previous unit. To recapitulate, in order to add a new element to the queue, we create a new node, copy queue data into the new node, set the link pointer of new node to null, set the rear pointer to point to the new node. To remove an element from the queue, we proceed like this. Create a temporary node pointer and initialize it with front pointer. Create a temporary node and copy the contents of head node to the temporary node. Reassign the front pointer to point to the next node. Delete node pointed to by temporary pointer. Return the copied information. Circular queue. In the circular queue, when the rear or front pointer gets to the last element in the array, it is wrapped around or reset to the first element, provided it is not already occupied. An example of circular queue is shown in the figure, which shows the initial state and subsequent states after addition and deletion of elements. Although inside the computer, the elements of the circular queue are stored consecutively in a linear order, it is intuitively more appealing to display them in a circle or ring shape as shown. In practice, the circular queues are more commonly used than the linear queues. Operating systems use circular arrays to implement the round-robin scheduling policy for process management. In computer networks, switches and routers use circular queues to store and forward packets of information. Array-based implementation of circular queues. You must have observed that the operations associated with the circular queues are identical to those on linear queues. However, there are few differences in the implementation of isFull and add operations because of overflow and underflow conditions. The overflow condition can occur in these circumstances: when the rear pointer is positioned at the last element of the array and the first element of the array is occupied, when front pointer is one element ahead of the rear pointer. These conditions are illustrated in the figure. Notice that in the first case, the rear is positioned at the last element with array index 7, while the first element of the array with index 0 is already occupied. In the second case, rear is positioned at the array element with index 2, while front is positioned at array element with 3. In both cases, it is not permissible to add a new element. Thus, in implementing the isFull and add operations, we must check for these conditions. Priority queues. The queue data structures which we have considered so far operate on the basis of first-come, first-served principle. There are, however, certain applications which require retrieval and processing of queue elements according to some prescribed order. For example, in some situations, it might be desirable to remove the last item first, bypassing all other items in the queue. The solution to such problems is provided by the priority queues. A priority queue, like an ordinary regular queue, is a collection of homogeneous data items in which items are added at one end and removed from the other end, but on the basis of priority. Thus, each item of a queue contains a data field and a priority field. The items within the queue structure are kept sorted according to the priority key. This figure shows an example of a priority queue. In the example, the queue consists of letters E, D, R, Z, and A with the priorities 1, 1, 2, 2, and 4 respectively. The elements will be removed in the same order. If another element, say Q, with priority 2, is added to the queue, it will be placed after the element A and before the element Z. The new state of Q is shown in figure. When a new element has the same priority as that of some of the existing elements, the principle of FIFO applies. For example, if an element T with priority 2 is added to the queue in figure, it is placed before Q, which also has priority 2, as shown. Applications of priority queues. Priority queues are often used by operating systems for managing and scheduling of processes in CPU. In preemptive multitasking operating system, tasks are placed in a priority queue which are processed according to their priorities. Programming languages supporting multi-threading use priority queue to control the execution of threads. In VLSI circuit design, channel routing and pin layout are efficiently manipulated by the priority queues. Priority queues are also used for controlling mission-critical applications such as industrial plants, nuclear reactors, or space vehicles. In an industrial plant, for example, working of various components is monitored and shown on the console. All events and associated messages are buffered in a priority queue. Appropriate actions on the processes with the highest priority are initiated immediately to take necessary remedial measures. Implementation of priority queues. Generally, a priority queue is implemented by using any of the approaches: array-based design, linked list design, binary tree, or heap design. The binary tree provides the most efficient implementation. For example, the time efficiency of array and linked list implementation is O of n, and that of binary tree implementation is O log n. Here, we consider the array design, which is comparatively simpler. Array-based implementation of priority queues. In this implementation, we assume that Q will be stored in an array of character strings with associated priority and sequence numbers. The C++ interface for the queue would look like this. Double-ended queue. An enhanced and more flexible version of queue is called DQ, which is pronounced as DEC or DQ. It is a collection of homogeneous data items in which data can be added to or removed from two ends. Thus, a DQ has the behavior of a stack as well as that of a queue. This figure shows an example of DQ. The second figure shows another state of the DQ after G and T have been removed from the queue and Z and W are added. Note that the order of the elements within the queue is not disturbed on account of new additions or deletions. To mark the ends of a DQ, two pointers, front and rear, are used. In some applications, it is necessary to restrict the entry or exit points of a DQ. A DQ in which addition can be made at only one end and deletion at both ends is referred to as input restricted DQ. Similarly, a DQ which allows deletion at one but addition at both ends is called output restricted DQ. Implementation of DQs. A DQ can be implemented using an array or linked list. In the array-based implementation, usually a circular array with two pointers variables, rear and front, are used. The size of array and type is fixed at compile time depending upon the expected number of elements and data type of queue items. When an element is added to the DQ at the front, the variable front is decremented by 1, and if it is added at the rear, the pointer is incremented by 1. Conversely, when an item is removed from the front, the value of front is increased by 1, and when an item is removed from the rear, the value of rear is increased by 1. When the queue is empty, the variables rear and front are set to null values. In the linked list implementation, the elements of DQ are contained in the linked nodes. Two pointer variables, rear and front, are used to mark the rear and front entries in the DQ. When an item is added, a new node is created at the head or tail of the list depending upon the entry point. Likewise, the head or tail node is deleted when an element is removed from the front or rear of the DQ.